So let me give you some examples. So this is an app that I personally worked on. It's called Shoppycat. It's about connecting people and products, and the idea is simple, right? I mean, so in the holiday season, people want to give gifts to friends and family. Now we all like to give very thoughtful gifts, right? When I give a gift to my friend, I'd like to give him a gift, a personal and thoughtful gift. I'd like to find out what he or she likes, and then give a gift that depends on that person's likes and dislikes. But the problem is we all have a lot of friends. It's very hard to keep track of what everybody likes and dislikes. So what Shoppycat does is that it uses social media like Facebook to figure out what your friends like and don't like. And then it combines that. So that's kind of semi-public data. Then it combines that with private data, which is a catalog of products from Walmart in this case, and sales data from that catalog, and it combines these two to recommend gift recommendations for your friends, right? So here's an example. So here's a guy who I don't know, but apparently he likes to run because he just finished running 5 miles. So the algorithm figured out that he would like running shoes, right? So there's another. He liked the Hunger Games, and the algorithm, figured out that he should get the Hunger Games cookbook, right? Things like this, right? So it's about taking semi-public information from somebody's Facebook profile, and then figuring out their likes and dislikes, and then figuring out what products they would like, right? So that's kind of a classic example of a 4th generation application combining private and public data to do interesting things, right? And so here's another example, right? So and this is once again from Walmart, where I worked most recently. There's this snack called Takis, okay? And this snack was kind of getting popular. Walmart, as you know, has stores all over the US, but this snack was getting popular, and the company wanted to know which parts of the country this is most popular in. So the stores in that part of the country should carry more Takis, and the parts of the country where it's less popular should carry less of this product, right? So there's no point having this product if people are not looking for it. So what the company wanted to find out was, where should we stock this product, right? There's no point stocking this product uniformly across the country because the demand for it is not uniform across the country. So what we did in this case was we went to Twitter, and we used the data that's on Twitter to figure out where are people talking about Takis, right? And we looked at kind of regional concentrations, and it turns out that there are certain parts of the country where people talk a lot about Takis. And then we sort of connected that with private information about Walmart stores and other information that we had, and we figured out which stores should carry Takis and which shouldn't carry Takis, based on data from Twitter and Walmart's own internal data, right? So this is another example. And you can see it's actually a snack that's getting very popular, more and more popular. That's the volume of Twitter mentions of Takis. You can see that it's increasing, but it's not increasing uniformly all over the country, but only in certain parts of the country. And you can use that information to figure out which store should carry this product and which store shouldn't carry this product, right? So this is a real example. Here's another example along the same line. Turns out that there's a snack that's getting popular. It's called a cake pop, right? Anybody know what a cake pop is? No. A cake pop is a cross between a cake and a lollipop. It's a cake on a stick. And it turns out that we found out, our algorithms found out by looking on Twitter that this particular snack is getting very, very popular, because you can see that nobody's talking about cake pops, nobody's talking about cake pops, nobody's talking about cake pops, suddenly everybody's talking about cake pops, right? So we figured out that cake pops are getting popular, and they were getting popular pretty much all over the US, all at once. And so this information will be passed on to the buyers at Walmart, and so Walmart now carries cake pop makers, so you can make your own cake pops at Walmart stores now. So this is actionable information from analyzing Twitter Twitter data. And you find out all kinds of interesting things about food and which part of the country likes apple pies and things of this nature by analyzing this public social information and combining that with catalogs and various other kinds of private information. So there's a lot of this kind of activity going on, creating a lot of business value today, and this is where I think a lot of the focus of the next generation of applications is going to be. Before we move on, a lot of people talk about big data, right? And I just want to, make it very clear that big data is not just about more data, right? I mean, there is clearly more data in the world today than there ever was. And in fact, the volume of data is growing faster than ever before, growing at 50% year over year, at least, maybe faster. But also, we're also talking about variety. We're talking about different kinds of data, like private, public, and semi-public. We're talking about tables. We're talking about Facebook, Twitter, text, HTML, image. So basically, there's a heterogeneity, a variety of new data that's available. Plus, the final thing that's just starting to be noticed is that the velocity of data is increasing as well, right? It's volume, variety, and velocity. Now, data is sort of moving faster than ever before. It's not that there's more of it, but it's flowing faster. For example, if you think about Twitter, or if you think about location data, if you think about location data from a mobile phone, right? It's going in real time from your mobile phone to Google or wherever it's going, or to Apple or wherever it's going. So your location is available in real time. And it can be, we were sort of starting to see a new generation of applications that can take data in real time and act on it in real time. And it's not as if you have a lot of time to analyze the data and do things with it. You have to take the data, analyze it, and get back in real time. And you're seeing more and more applications of this, of this kind of nature, where you have this kind of fire hose model of data coming to you. You have to process the fire hose really, really quickly, and you have to get back, right? So you're going to, so there are lots of applications of this kind as well. I don't have time in today's talk to go through those kinds of examples, but there are lots and lots of applications that are about real-time data processing as well. Are we stuck? Now, I'm sort of ending this part of the talk. I'm moving on to the next part of the talk, which is about how to succeed in a data-rich world, but it looks like I have a problem here. There you go. Okay. Now, this part of the talk is a little bit more technical than the first part of the talk, please bear with me as I go through this. So far, the world that we've lived in, right, is what I call a data poor world. There's been a relatively small amount of data in the world compared to the amount of data that we're seeing today. And a lot of our methods for designing applications and of using data are designed for this data poor world. Okay? And they just don't work in a data-rich world. Okay, so let me sort of explain this to you using some examples as we go along. So here's how we sort of use data in most data-driven applications, right? In computer science, or in machine learning. So what you do is you take data, whether the data, if data could be purchase data on Amazon. Or market basket data, whatever it is, you take a bunch of data and you sort of analyze the data and you build models with the data. And there's all kinds of machine learning algorithms people use to build models of the data, right? You might use neural nets or regression or various kinds of classifiers or decision trees. There's all kinds of algorithms, fancy algorithms, support vector machines. There are all kinds of fancy algorithms. But at the end of the day, what all these algorithms do is that they take the data and they create a model. And once the model is built, okay, the data is thrown away. You ignore the original data, and then you work with the model. And then when you get a new problem, you use the model to make a prediction, right? So for example, let's use an example, right? So let's say you're doing an application on fraud analysis. Let's say this is an application that looks at credit card swipes. Let's say you swipe a credit card at a point of sale system, and the system has a model of fraudulent activity. It sees that the same credit card has been used in multiple places at the same time and so on, and it has some kind of model. And if it sees something is suspicious, it says, look, don't honor this credit card swipe because it looks like it's a fraudulent swipe, right? And the system has a model that sort of tries to guess when a credit card swipe is good and when it's bad. Right, so this is a simple example of a fraud detection system. But you can sort of think of many systems where you sort of take data, you build models, and then use those models to do interesting things in the real world. So this is how most systems are built that deal with data, right? Ignoring exactly what kind of model you're building and what algorithm you use to build it and so on. Let's see whether I can get this thing to move. So these these methods, if you think about them, the problem is the following, right? So you take the data and you build these models, right? And let's say let's say you're doing credit card swiping. Let's say credit card swiping, for instance, right? You are at 95% accuracy and you want 97% accuracy. You want to improve your accuracy, right? So what do you do when you want to improve your accuracy? Well, you build a more sophisticated model, right? So what you do is that you try to build a more sophisticated model. You take more parameters and you build a bigger model that has more features and so on. And then you go from 95% accuracy to 97% accuracy. Let's say you want to go from 97% accuracy to 98% accuracy. What do? You build a bigger model, right? So the problem is bigger and more sophisticated models, right? To get more and more accurate, you have to build more and more sophisticated models. Now, one of the interesting things that you realize when working in the real world is that sophisticated is just another way of saying complex. And complex systems tend to break down. Okay? So as you make your model bigger and more sophisticated and more complex, it gets more and more brittle. The more complicated a model gets, the more brittle it is, and the more susceptible it is to changes in the real world. Right? So when the real world changes and the model doesn't reflect it anymore, then the model breaks down and you get bad predictions. So for example, if you think about one classic example is the financial meltdown that we had in the around 2007 or 2008, when a lot of companies were doing lending or derivatives trading based on certain models, and they were doing algorithmic trading based on these models, or lending people money based on these models. And these models were pretty sophisticated. But then the world changed and the models didn't work, and we had a big financial crash, right? So basically the models were not modeling the real world because they were they were getting more and more complex, but they were not modeling the real world. So as models get more and more complex, there's a chance that they don't model the real world at all. And the more complex the model, the more the chances of that. Right? The simpler the model, the more likely it is that it's not going to be very badly off. Right? So that's the problem that we have, and we've seen really bad outcomes, like the big financial crash we had were pretty much caused by these problems. And the more and the underlying problem here is that the more complexity you put in a model, the longer it takes to adapt to a new and changed world. Right? The world changes too fast to build too complex models, really. So that's really what's going on in the real world. So what these are what we really need today in this era of rich data, or what I'll call model light, light models, but heavy use of data. Right? Let me show you an example to show you what I mean.